lecture will probably be a little shorter than the others. I guess you're all anxious to stop, and for those of you going to the excursion. So, the last two methods I want to present for looking for computing for trying to find what one can compute on the Mordell-Weil group of an elliptic curve. I talked about 2 descent and 3 descent, higher descents. So one is really very, well, I wouldn't say naive, but it's really extremely easy to set up. But unfortunately, it only gives you partial information, but extremely important partial information, which is just the rank. It doesn't give you the generators, but at least it gives you what is certainly going to be the right answer on the rank, at least if you assume the Birch-Swinnerton-Dyer conjecture. I guess you have to assume slightly more. Anyway, so this is the use of the L function of the elliptic curve, and I will remind you what the L function is. We assume that we have a minimal Weierstrass equation over Q. I don't want to define this term, but there is a way, using Tate's algorithm, to obtain an equation whose discriminant is as small as possible at every prime. I mean, the prime power is as small as possible. And this is possible only over number fields such as Q, where the class number is 1. If you have number fields of higher class number, there doesn't need to be a global minimal equation, but here it's possible. So you take such an equation, you say that it has good reduction at P, of course, if P does not divide the discriminant. And you define A sub P equal P plus 1 minus the cardinality of E of Fp, and chi of P equals 1, when, indeed, the reduction of the elliptic curve modulo P is still an elliptic curve over Fp. So that's A sub P, and by the Hasse bounds, we know that A sub P is less than or equal in absolute value to 2 square root P. Good. If P has bad reduction, then there is a recipe. First of all, we set chi of P equals 0 in that case, and then you set A sub P equals 0 if there is a triple point, y squared equal f of x. In that case, that means that f has a triple root. Or, well, that's called additive reduction by the experts. Or AP equals, well, it's called additive reduction because, in fact, the group of points of your elliptic curve over Fp is now minus the singularity is isomorphic to the group G sub A of the additive group. AP equals 1 or AP equals minus 1 if there is a double point with or without irrational tension. This is called split or non-split multiplicative reduction. But in fact, this recipe, which is in fact the correct way to present this recipe, you still have A sub P equal P plus 1 minus minus the cardinality of E of Fp in all these cases. Anyway, you define the global L function of the elliptic curve, L of E sub comma S, as the product over all primes of this local factor, 1 over 1 minus A sub P, P to the minus S, plus chi of P. Chi of P, remember, is 1 or 0, times P to the 1 minus 2S. Now, there are many good reasons for which you want to define L of ES in this way. One of them is that it's a part of the Hasse-Weil zeta function associated, the Euler factor, which is here, is the non-trivial part of the Hasse-Weil zeta function of the elliptic curve over Fp. There are other reasons, but anyway, this is the global L function. Because of the Hasse bound, it converges for a real part of S greater than 3/2. So we have a nice holomorphic function. Yeah, it converges, and of course it defines a holomorphic function in that half plane. And of course, the crucial theorem of Wiles, Taylor-Wiles, and successors is that this function can be extended to a holomorphic function in the whole complex plane, having a functional equation of the form lambda of E and 2 minus S equal epsilon of E times lambda of ES, where epsilon is called the root number. It's equal to plus or minus 1. It's algorithmically computable, although the algorithm for it is extremely tedious. It involves something like 140 different cases. So when you program it, you really have to be careful not to make a single mistake. It has been programmed. GP was the first language in which it was programmed. I think there is no mistake. Well, nobody has reported any mistake after the first few months of use. Lambda of ES is a gamma factor times the L of ES. Precisely, it's a given integer n, which is called the conductor, which is divisible by all the primes of bad reduction at certain powers, which can be computed by Tate's algorithm. I don't want to enter into that. To the power s over 2, 2 pi to the minus s, gamma of s. L, well, okay, that's the gamma factor. And so Weyl's theorem tells us that this function has a functional equation, which I wrote. Now, of course, there are many equivalent ways to state Weyl's theorem. Those of you who have had a course in modular forms recognize, of course, that the gamma factor in front of L of ES is exactly the gamma factor in front of the modular form of weight 2. Well, weight 2 because of the functional equation. So indeed, another way to state the theorem of Weyl's is to say that the modular form sigma of a sub n q to the n is a modular form of weight 2. I will come back to this in the next slides. Okay, so all of this is easily computable. But what is extremely important, there is one thing which is not at all clear, and non-experts sometimes do not know. Okay, because of the Birch-Swinnerton-Dyer conjecture, to which I will come back, of course, we're interested in the value at 1. Remember, the value at 1 is something which we know exists only thanks to Weyl's. L of ES is defined for real part of S greater than 3/2. So the value of at 1, what was this famous quote already about the Birch-Swinnerton-Dyer conjecture before Weyl's was proved? That it related a number. It related the value of a function at a point on which one didn't know the function was defined to a group, which was the Tate-Scheffer-Heritage group, which we didn't know was finite. I mean, it was a completely crazy conjecture at the time. Anyway, I don't know who. It's the famous quote. Tate? Okay. Anyway, now this has become a little more palatable thanks to Weyl's. So if the root number is equal to -1, of course, the value at 1 is equal to 0, so it's not very interesting, although I'll also come back to that. Otherwise, it's really something very amusing, and the students should be aware of this. As soon as this has absolutely nothing to do with elliptic curves. If you have a function, a Dirichlet series, having a functional equation with standard gamma factors. Now, the gamma factors don't need to be of this form. You can take many gamma functions in front and so on. As soon as you have such a function, you can compute it explicitly using an exponentially convergent series. It's an automatic consequence of that. It simply uses complex integration. It's extremely simple to prove, but it's a very good exercise in undergraduate complex integration. I repeat, it's totally automatic. And in our special case, we have the very, very simple formula that L of E1, of course, in the case you want to compute L of E1, which is when epsilon of E is equal to +1. If epsilon of E is equal to -1, this formula is false, but we don't want to compute it. It's 0. Then it's simply equal to this sum, sigma of A sub n over n e to the -2 pi n over square root of n. I would like to point out two things here. First, I may have forgotten to tell you what A sub n is. Well, L of ES, I guess I forgot to write, but I write this as a sigma of A sub n over n to the s. Okay, that's, I guess, clear. Second remark, you see the exponential here. It's e to the -2 pi n over square root of n, and this is a very important thing. That means that if the conductor is large, of course, it's exponentially convergent, but still, you're going to need at least square root n terms to get just two decimals. And of course, if you want to get 10 or 20 or 30 decimals, you'll need maybe 10 square root n terms. But at least it's square root n. It's not n, so that's already a better situation. You can manage up to 10, n equal 10 to the 9, maybe, or 10 to the 10. But it starts to get a little painful. But in any case, it's exponentially convergent. No problem. Okay, so now let's come to the Birch-Swinnerton-Dyer conjecture. There is a very precise statement. I do not want to state it. No use. You can find it, of course, everywhere in the number theory universe, including in my notes or other places. In my personal opinion, it is the most beautiful conjecture in the whole of mathematics, not even number theory, but that's a personal opinion. Okay, it tells us that there are non-torsion points on E of Q. In other words, E of Q is infinite if and only if L of E1 is equal to 0. It's really a very, very nice statement. In fact, it's much more powerful than this, but I will come to this. It tells us much more than this, but I will come to this in the next slide. Unfortunately, except in rank 1, which is exactly the Heegner point method, to which I will come afterwards, and which is the subject of the student presentation, one doesn't know much about this conjecture, and it doesn't help us in finding the points. So what is known essentially due to Rubin, Kolyvagin, I don't want to miss attributions, I'm sure there are many other people. Gros-Zagier, of course, did I forget them? Oh, that's a shame. Excuse me, of course, Gros-Zagier. So what is known is if the analytic rank is 0, excuse me, oops, there is a big misprint here. Excuse me, of course, the first line is completely wrong. If L of E, that's because I'm getting tired. If L E comma 1 is different from 0, then there are no non-torsion points. The group is finite in that case. Excuse me, it's different from 0 in the first line. If L of E1 is equal to 0, but the derivative at 1 is different from 0, so that means that the analytic order, the order of the 0 s equal 1 is exactly equal to 1, then the algebraic rank of the elliptic curve is exactly 1. And in particular, there exist non-torsion points, which can be found using the Heegner point method. On the other hand, if L of E1 is equal to 0 and L prime of E1 is equal to 0, meaning that the analytic rank is at least equal to 2, the order of the 0 at 1 is at least 2, then we conjecture that the rank is in fact equal to the analytic rank, so the rank should be at least 2, but one knows nothing. The rank could be 0. We don't know anything. It's very frustrating. So, I'm skipping. Well, no, I'm not skipping. I forgot to write one line, which I will say now. So, as I said, the Birch-Swinnerton-Dyer conjecture tells us more than this. It tells us that the rank of the order at s equal 1 of the L function should be equal to the rank of the curve, the rank of the more elevated group, and that is really the statement that we would like to prove. It says even more than that. It gives you the leading term, but simply knowing that the rank. Okay, so using L of ES, you get a reasonable conjectural value for the rank, which you are almost sure will be true. So you compute, how do you do this in practice? You compute first the root number. This is totally algorithmic. You don't need the analysis for this. So assuming the BSD conjecture, this tells you already the parity of the rank. If the root number is equal to +1, the rank has to be even. If the root number is -1, the rank has to be odd. And then you compute the L function at 1 at the derivative, the second derivative. Of course, you compute only 1 out of 2 because half of these derivatives are trivially 0 once you know the parity. And you compute this numerically using exponentially convergent series. I just gave you the one for L of E1, but there exists exactly analogous series also for derivatives. Instead of using the simple transcendental function exponential function, it uses some higher transcendental function, but everything is under control. One knows how to compute these things very fast. So there is absolutely no problem to compute that the third derivative is equal to 0 or whatever. This to as many thousands of decimals as you want. And this really gives you a handle on the rank. You know what the rank is conjecturally, but that's all you know. You don't. Okay, so now let's come to the Heegner point method, which is really the high point of computations of rational points over elliptic curves, which will be the object of the student presentation. I hope I'm not going to, well, I hope what I'm going to say is not going to intersect too much with what they are going to say. I don't want to spoil their presentation. So it's a remarkable way to use the L function to find a non-torsion rational point. And this can work only when the rank is really exactly 1. So there are two tools which are used. One is complex multiplication, and the other is the modular parameterization given by Wiles et al. Of course, for the algorithm, you only need to understand the theorems, but you don't need the proofs, that's clear. And in fact, don't forget that we're just trying to find a rational point on an elliptic curve. So you can assume any conjecture in the world that you want. And in fact, there is an algorithm, but I must say I'm not very familiar with this. I've heard of this algorithm for 20 years. It's called Manin's conditional algorithm. I have no idea what this algorithm does. If somebody can explain. Anyway, you can assume any conjecture you want to construct the point, since at the end, once you have the point, you can check whether it's really a rational point on the curve. Okay, so the setup is as follows. You have an elliptic curve defined over Q, the L function, which I write as sigma of an n to the minus s. So let's start with the modular parameterization. Wiles' theorem tells us that, in fact, as I mentioned, if you take the function f sub e of tau, which is sigma of an q to the n, q is the usual q used in modular forms, e to the 2I pi tau, then this is a modular form of weight 2 over gamma naught of n. The definition of modular form is very simple, but I don't need to recall it, because in fact, this is equivalent to saying that 2I pi f sub e of tau d tau is a holomorphic differential which is invariant under gamma naught of n up to the period lattice of f sub e. So the natural thing to do in that case, you define phi of tau equal 2I pi, well, that's for suitable scaling to get rational values. The integral in the complex plane from I infinity to tau, well, I infinity is up there, of f sub e of tau, of z dz, and explicitly this is this series, which converges rather fast also if q is not too close to 1. Doesn't depend on the chosen path since the differential is holomorphic, and defines a map, because it's invariant under gamma naught of n, it defines a map from the quotient of the upper half plane, which I call script h, divided by gamma naught of L of n, to the quotient, oh, my color coding went wrong here, blue c divided by lambda, since of course I have to divide by the period lattice of f. Now, h over gamma naught of n has cusps. It's not a very nice thing. You have to take its closure. You have, in fact, to take h union the projective line over q divided by gamma naught of n. And this defines a much nicer curve called x0 of n. And it's extendable to a map from x0 of n to c over lambda, except that the formula, which is up there, you cannot use the formula on the right. You have really to use the integral on from one cusp to another cusp. Anyway, that's no problem. And lambda is the lattice generated by what are called the periods of the modular form, which are the 2I pi integral from one cusp to another of the modular form. Now, there is a slight technical stuff here. I don't want to enter into it, but since I don't want to say something wrong, usually the lattice lambda is a sublattice of lambda e, which is the lattice associated to the elliptic curve. Remember, an elliptic curve over C is the points of an elliptic curve over C is isomorphic canonically with the Weierstrass p function to C divided by lambda e. So usually you have lambda's sublattice of lambda e. In fact, usually you even have equality. But there may occur cases, I mean, there is something called the Manin conjecture. Well, one of the numerous Manin conjectures. Here it's the deals with what is called the Manin constant, and it's conjectured that the Manin constant is always equal to 1. Well, I don't want to enter into these technicalities. Let's assume in practice, in fact, in all the millions of cases which people have computed, we always have this. But it may happen that it's not the case. But if it does happen, it's very easy to deal with. So I don't want to enter into these details, just to mention that they exist. So we get a map from x naught of n to c over lambda. And now, once you're in c over lambda, I wrote incorrectly that E of c is equal to c over lambda. That's not quite true. It's isomorphic. And the isomorphism is given by the Weierstrass p function, which sends a complex number to, well, p of z. And the elliptic curve is parameterized by p of z and p prime of z, the derivative of the Weierstrass p function. So when you compose all this, you get a map from x naught of n to E of c itself, which I denote now with a var phi sign. I don't know how to say this in English. In tech, it's called var phi. Well, I mean, it's another phi from this upper one. And this is called the modular parametrization, by whilst this thing exists and is unique up to sign.
Are you assuming that E has no Cn?
No. Why? If it has Cn, it's not unique? Is that what you... I think it's unique.
Can you just compose it with a multiplication map?
Yeah, I mean, you can compose it with the Cm map of...
Oh, that's right. Okay, so it's not always unique. At least it exists. Okay, now that was the first tool that we use in Heegner point. The second tool is complex multiplication. We'll say that tau is a Cm point if it's in the upper half plane, and it's a root of the quadratic equation ax squared plus bx plus c equals 0, where a, b, and c are integers, whose, of course, discriminant b squared minus 4ac has to be negative, since tau is in the upper half plane. We can make this unique by requiring that the GCD of a, b, and c is equal to 1 and a positive. Then we call the discriminant of tau, delta of tau, is, of course, b squared minus 4ac. And, of course, you can write tau as minus b plus square root of delta divided by 2a. So the basic result of complex multiplication in our context, there are several ways in which to state this, is that if tau is a suitable Cm point, not every Cm point works, then in fact phi of tau, where phi is the modular parametrization that I just mentioned, in fact is an algebraic point on our elliptic curve. Of course, phi of tau is in E of c, it's on the elliptic curve, but not only is it with just arbitrary complex coordinates, but in fact its coordinates are algebraic, which is completely miraculous. And in fact, you can state very precisely in what algebraic number field the coordinates will belong. They will belong to the Hilbert class field of the imaginary quadratic field k equal q of square root of d. If you don't know what that is, it's not very important. It's just some algebraic extension of k, which is usually not very large. And this is the magic of complex multiplication, of course, is to create algebraic number using analytic functions. This occurs in several places in modern mathematics. And it was Kroneker's dream of use to do this for other number fields than imaginary quadratic fields or Q. I guess the only real progress on this was made by Stark's conjectures. But we are, of course, extremely far from this dream. Anyway, for us, we're just on imaginary quadratic fields, so complex multiplication works very nicely. Okay, so now let's go down to business. That was the preliminaries. We needed modular parametrizations and we needed Cm. Okay, those are out of the way. So now let's go down to Heegner points. So Heegner points were apparently invented by Heegner, but the presentation I'm giving here is essentially due to Brian Birch. So it has, of course, become very, very classical now. So we'll assume for simplicity that the discriminant of tau is a fundamental discriminant, is a discriminant of the quadratic field. It's very easy to modify for general discriminant, but this is slightly simpler. So we're given n, capital N, which is the conductor of our curve. and we'll say that tau is a Heegner point of level n if one of the following three equivalent conditions are satisfied. The discriminant of n times tau is the same as the discriminant of tau. And then if you want to put it really in down-to-earth terms, it means that n divides a, and the GCD of a over n, b, and c times n is equal to 1, or n divides a, and b is congruent to b squared modulo 4n. These conditions are trivially equivalent. Warning, they are equivalent because I assume that d is the discriminant, a fundamental discriminant. If d is not a fundamental discriminant, you have to add a slight side condition. Okay, now the basic property of Heegner points, of course, is that if you have a Heegner point, and if you have an element of gamma naught of n, by the way, I realized that I didn't define gamma naught of n for you, but I guess that everybody knows what it is. It's 2 by 2 matrices over SL2Z, whose left-hand side coefficient is divisible by n. Then gamma of tau itself is also a Heegner point of level n. So what in fact will interest us is not really Heegner points of level n, but classes of Heegner points of level n modulo the action of gamma naught of n. Other operators which preserve Heegner points of level n, one is the so-called Fricker involution, W of tau, which is simply minus 1 over n tau. And more generally, you can define what are called Atkin-Lehner operators, W sub q, for any q which is a prime power divisor of n. And these points are, again, Heegner points of level n. This remark is, okay, what is basic is the first line. The next two lines are important to speed up the algorithm, but are not crucial for the existence of the algorithm itself. It enables you, the use of these extra operators W enable you to reduce the amount of computation you need to do. Now, I recall that from Gauss, well, no, this is not quite true. But anyway, it's the extremely classical theory of binary quadratic forms and ideals in quadratic, in imaginary quadratic fields is that there is a natural one-to-one correspondence between SL2Z classes of binary quadratic forms. I remind you that I am in the case of a fundamental discriminant, so you don't need to add the word primitive, otherwise you would have to. And the ideal class group of the corresponding imaginary quadratic field. I didn't write imaginary. So this is a very well-known correspondence, which, well, essentially dates back to Gauss, except that, of course, Gauss didn't know what an ideal was. This can be easily generalized to gamma naught of n, and it's very amusing because, in fact, the correct generalization gives you exactly the definition of the Heegner point. I mean, it's the only right way to generalize to gamma naught of n. So you define, you take the set of binary quadratic forms whose first coefficient is divisible by n, and with the condition, the additional condition that a over n comma b comma c times n are global ecoprimes. And it's on that gamma naught of n acts, and there is a natural correspondence between gamma naught of n equivalence classes of Heegner points. Think, instead of Heegner points replaced by what I just said, binary quadratic forms satisfying this condition of discriminant d on level n. And now, not ideal classes, a little more precise than that, pairs of an ideal class A and an element beta defined modulo 2n such that beta squared is congruent to d modulo 4n. I remind you that d is always congruent to a square modulo 4n in the Heegner point situation. And of course, if beta is defined modulo 2n, its square is defined modulo 4n. So this is a completely natural one-to-one correspondence, which is exactly the generalization of the correspondence between classes of binary quadratic forms and ideal classes of imaginary quadratic fields. It's very simple, very easy to prove. So the main theorem of complex multiplication, a reformulation of what I said, let's take tau. So now I can consider a Heegner point. Oops, there's a misprint. Tau is not beta class of alpha. It's, of course, beta class of A. Excuse me. The alpha in the first line should be A. Let's take tau a Heegner point of discriminant D, fundamental for simplicity, but it works in general. Level n, K, the imaginary quadratic field, H, the Hilbert class field. So here I added some few words. tell you what it is, the maximal unramified abelian extension of K. I guess it won't help you because... And the Galois group of the Hilbert class field over K is isomorphic to the class group of K through the Artin map. If you know what it is, then you won't have learned a thing, and if you don't know what it is, I don't think you can learn in 1.5 line. So recall that phi is the modular parameterization from x mod of n to blue E, which I forgot to put in blue. Then the fundamental reformulation of the fundamental theorem of Cm, which I need, is that phi of tau belongs to E of h. I already stated this fact. That's the algebraicity result. The second result, which is also extremely important, gives you all the conjugates of phi of tau. This is Shimura reciprocity. It's called Shimura reciprocity. If you take an ideal class in CL of K, then the Artin map, you may not know what the Artin map is. The only thing you need to know is when you take the Artin map of all ideal classes, you get all the possible conjugates, all the possible elements of the Galois group. So that gives you a formula, an explicit formula. You see, you get beta comma A, and here beta A B inverse. So this is an explicit formula giving you all the conjugates of the point which is over some bigger field, capital H. So it's a very nice, completely explicit formula. Remember, all these things can be computed by exponentially convergent series. You also have formulas for phi where you act with the Fricker involution W or with the Atkin-Lehner operator WQ. This is technical, you don't need this. And you also have a formula giving the complex conjugate of phi in terms of the inverse ideal class. Now that's very interesting, for instance, because it immediately enables you to cut the computation time in two, because, well, let's forget, okay, in the class group, well, the class group may have, assume for instance the class group is of order 5, well, then you can pair class with an opposite class, with an inverse class. Of course, there will be some classes whose square is equal to 1, so that you can't pair. But the others, you can cut the work usually, if I'm not mistaken, yeah, if well, okay, you understand what I'm saying. Because of this formula, you can, since we will need to compute phi for every ideal class, this divides the work in two. You simply take complex conjugates. Okay, and as a consequence, you can compute the trace, since we know all the conjugates of phi, you can compute the trace of phi of tau on the elliptic curve. Warning, of course, the operation that I'm doing here is the operation on the elliptic curve. In the algorithm itself, in fact, one does it before taking the modular parameterization, so one just does addition on the complex numbers. But what you need to see is this. So we define the point P as the sum of all the conjugates on the Galois group. And by Galois theory, this point is going not to belong to E of H, but to E of K. But thanks to Shimura reciprocity, this sum is simply equal to the sum over ideal classes of this quantity. And since multiplication by B inverse, or by A, excuse me, and of course inversion, all these are bijections from the class group to itself, this is simply equal to the sum of phi of beta B over simply the class group. And the sum, as I said, being computed using the group law. So by Galois theory, P automatically now is a much lower number field. Its coefficient are in the imaginary quadratic field K. And it's a very easy exercise in Galois theory to show that, in fact, in our case, where the root number is equal to -1, in fact, P immediately lies in Q. Already its coefficients. It's an E of Q, has rational coefficients, which is exactly what we want. So, final slide on the Heegner point method. Thanks in particular to the theorems of Gros-Zagier and work of Kolyvagin and so on, it's known that if P is that P, the point that you obtain at the end of this process, is non-torsion if and only if, first of all, the rank is equal to 1, and I think I repeated this often enough. This is already known. And you need a condition that the L function of the twisted elliptic curve, E sub d at 1, is not equal to 0, where E sub d is the quadratic twist of E by d, whose equation is dy squared equal xq plus ax plus b. Hence, when you do the algorithm, the first thing you do, before doing all the computation of modular parameterizations and all that, first thing you do is to compute L of E sub d, comma 1. If it's very close to 0, just forget it. Go to the next. So the point P that you obtain in this way is usually a large multiple. You see what I wrote. It's really if and only if. So if these conditions are satisfied, then you know that your point P is of infinite order. It's really nice. So, however, even though it's in infinite order, it's usually a large multiple of a generator. And so it's very difficult to recognize as a rational number. But you can reduce it considerably by using the theorem of Grosset. And you get a very nice algorithm. So as a very classical example, due to Zagier, if you consider the congruent number problem for n equal 157, this corresponds to the curve, elliptic curve y squared equal x cubed minus 157 squared x, which has rank 1. It's a reasonably large example already. And in about a couple of minutes, you find a point P with numerator and denominator of x and y. Excuse me, why did I put of x? No, that's a mistake. X and y, having up to 36 decimal digits. For details on all this and this particular example, I refer you to the student presentation. Okay, I will finish my series of lectures by 3 slides on the computation of integral points, and then I will stop a little ahead of time. So we assume now that we have computed the Mordell-Weill group, we have computed the rank, and we have computed a system of generators. Of course, that's a big assumption. As I mentioned, there is no general algorithm known to do this, but in many cases you can do it, so let's assume that you have done this. So now our goal is to compute the integral points, not only the rational points, E of z. Now, a very important warning from the very beginning, this question doesn't make sense. I shouldn't call it E of z. Because E of z means that it's something which depends on E and on z. Well, that's not true. Well, it certainly depends on z, but it doesn't only depend on E. It depends on the model that you have chosen for the elliptic curve. If you take an equation, y squared equal x cubed plus ax plus b, okay, that's one model. But then you can make some coordinate transformation, you get another model, and the integral points in that other model are not the same as the integral points in the first model. So the integral points depend really on the model. On the other hand, the rational points do not. Okay, but anyway, let's forget this. We have a given model. So by abuse of notation, I will write this as E of z. So if you have a point on E of z, which is a subgroup, subset of E of q, of course, the integral points don't form a group, it's just a set. By the way, there is a theorem of Siegel, I forgot to mention, which says this theorem is not very difficult, but it's not very easy either, which tells you that the set of integral points on an elliptic curve is always finite. And as far as I know, this theorem is non-effective. It's finite, but you cannot give it bound on. You can give it bound on something?
If you use Baker's.
Oh yeah, that's my next slide.
Okay.
Okay, so you can write P in the form T plus sigma of xi pi, where T is a torsion point and xi are integers, since of course this is the structure of the Mordell-Weill group, so you just write the decomposition on the free part and the non-free part. And it's a very easy exercise to show that if you call capital H the maximum of absolute values of these coefficients xi, which are of course the things you're looking for, then in fact the absolute value of x, there is a, well no, it's not a misprint, but I didn't explain what x is. X is the x coordinate of P. P is equal to xy. Excuse me, I wrote these slides an hour ago, so x has absolutely no relation with the xi's. The xi's are the coefficients of pi's, while x is the x coordinate of p. Please, I'm sorry for this confusion. Anyway, it's a very easy exercise to show that the absolute value of x is bounded from below, at least if x is non-zero, of course. You may have points with x equals 0. Those are very easy to find. X is bounded from below by a constant times an exponential in h squared. Okay, this is very easy. I mean, this is not Baker. It's really very, very easy 5-line computation. Now, the second tool we need to use, now it's clear that I wrote this very, very fast, lots of colors and parentheses missing and so on. Okay, anyway, the second tool we're going to use is the elliptic logarithm. Now, you shouldn't be panicked by this name. It's really a fancy name for something which is nothing. Remember that we have a modular parameter, that we have the standard parameterization given by the Weierstrass P function from the lattice C over lambda to the elliptic curves given by P prime, okay? That's called the elliptic exponential, okay? Because it has, in fact, properties analogous to the exponential. And the elliptic logarithm is exactly the inverse map. So it's the map which goes from a point on the elliptic curve to the z. That's all. That's called psi. Okay? So it goes from E of c to c over lambda. If you want, it goes from E of c to c. And in that case, it's defined only up to addition of a point of the lattice. It's exactly like the ordinary logarithm, which is defined up to an element of the lattice generated by 2i pi. So here, it's a two-dimensional lattice. So, in fact, there is what you can call a principal determination of the elliptic logarithm. The only values of the elliptic logarithms which we're going to use are real. The elliptic curve, real elliptic curves, which is our case here since we're over Q, have a fundamental domain where there are two periods. One is real, and the other is either purely imaginary or having real part exactly equal to half of the real period. Anyway, it's only the real period which interests us, and what we will call the principal determination of the elliptic logarithm. You can always manage to have the elliptic logarithm between minus 1/2 of the real period and plus 1/2 of the real period. So an absolute value less than or equal to 1/2. Anyway, so all this is very similar to the ordinary logarithm. And as a consequence of the above result, which I mentioned, you can easily show that when x is sufficiently large, everything is explicit in what I'm saying, then the absolute value of the elliptic logarithm at p is less than or equal to a constant times an exponential of minus h squared over 2, the same constant c2 that occurred before. Everything is explicit here. And I said if you choose psi of p as small as possible, meaning between minus omega 1 over 2 plus omega. Now, this is where Bjorn's, of course, remarks comes in. On the other hand, you have Baker's theory. Baker's theory is extremely powerful and has been generalized to the elliptic case by many people, and the best bounds have been obtained by Sinu David, who obtained bounds on linear forms in elliptic logarithms. Whatever that means, it enables us to get an inequality for the logarithm of an integral point, psi of p, which is in the other direction from this one. I'm not giving it because it's too technical. But what you must assume, from what I'm telling you, is that this inequality in the other direction contradicts this upper bound, which is really very powerful. I mean, look at this upper bound. It's e to the minus h squared. This tends to 0 extremely fast in h. While the lower bound given by Baker, well, by David, tends to 0 also, but much slower than that. So, you get a contradiction for h sufficiently large. Everything I'm saying is, what is very important, all the constants in what I'm saying are computable, effective, everything, no problem. They're very large, sure. So you get an upper bound for h, and as usual, in this type of Baker-type computation, the upper bound that you obtain is pretty large, but not ridiculously large. In a typical application for elliptic curves, you get that h is less than 10 to the 100. Remember that the h is already quite nasty because the h is the coefficients of the pi's. So, well, okay. Anyway, so you get some bound like 10 to 100. So now what do you do? Well, after all, the rank may be only 2 or 3, so you only have about 10 to the 300 cases to consider. It's a little too many. Sorry. These slides were written only an hour ago, as I said. So, of course, 10 to the 80 and 10 to the 100, I just forgot some curly brackets. So it's absolutely essential that Baker bounds be explicit. On the other hand, it's absolutely not essential that they be sharp. It doesn't matter whether you find 10 to the 80, 10 to the 100, 10 to the 200. Who cares because of what I'm going to say? Well, it shouldn't be 10 to the 10 to the 100. But on the other hand, just a factor like that, orders of magnitudes are not important. Why? Well, because there is a magical algorithm, absolutely magical, which has been mentioned several times already this week, which is the LLL algorithm. The LLL algorithm finds small vectors in lattices, sure, but this allows you either to find linear dependence relations between complex numbers. Well, this was used by Dan's talk, in fact, if I heard correctly, or to show, and that's in fact our application, that if you have some approximate relation between real or complex numbers, then in fact the coefficients must be bounded by something. Very effectively. And the consequence of this, bounded, excuse me, I forgot the crucial word, bounded, excuse me, I'm tired. No, it's okay. Now, what is crucial in this, and it's really completely magical, is that thanks to this, you obtain a logarithmic decrease in the size of the upper bound. And that's why I don't care at all whether I have 10 to the 80, 10 to the 100, 10 to the 200. Because the next step, I'm going to use LLL and reduce this by a log. I'm going to take the log of this. So the log of 10 to the 200 is the same as the log of 10 to the 80, I mean, as far as I'm concerned. So let's take an example. This is my last slide. This is a famous elliptic curve, y squared plus y equal x cubed minus 7x plus 6. Why is it famous? Because it's an elliptic curve of rank 3 with the smallest conductor. That has been shown by Cremona. Well, it was shown much before Cremona that it had rank 3, but it is the smallest. Conductor 5077. And it's important because there was a beautiful theorem of Goldfeld who showed that if you could find an L function with suitable properties who had a 0 of order 3, excuse me, a 0 of order 3, at least 3, then you could find effective lower bounds for the class number of imaginary quadratic fields. And before the work of Gros-Zagier, no such functions were provably found. And thanks to Gros-Zagier, this function, you can prove, has analytic rank at least equal to 3. The proof is very simple. I leave you using, of course, what one knows about the Birch-Swinnerton-Dyer conjecture. It's very simple, although I did tell you that the Birch-Swinnerton-Dyer conjecture is known only in rank 0 and 1. You can deduce this, you can use this to prove that this has analytic rank 3, which is what you need for Goldfeld's theorem. Anyway, that's not our goal here. So on this curve, let's try and find all integral points on this model. Using the bounds of David, you find that the largest of the pi, of the xi's, the coefficient xi in absolute value, is less than 10 to the 60. As I mentioned, if you found 10 to the 100 or 200, I wouldn't care. Now, using LLL, you see, this is absolutely incredible. Using LLL, you reduce this to h less than or equal to 51. I mean, if you've never done this in your computer, it really takes 5 minutes to program on any reasonable computer which has LLL or even which doesn't have LLL, because the programming of LLL is so easy. Okay, now the amount of work becomes, of course, extremely reasonable. But after all, why not? Why stop there? You can use LLL a second time, and this reduces to h less than or equal to 11. But of course, it's the law of diminishing returns. You can use LLL a third time if you want, but it reduces 11 to 10, which is not very interesting. And then if you go on, it doesn't improve. Anyway, now you can do a direct search. You have less than 10,000 points to test, and you find 36 integral points exactly, and you have proved that you have only 36 integral points. Now, this is quite a large number of integral points, and it's a phenomenon which is partly understood, but not completely. If you take an elliptic curve with the smallest conductor having a given rank, you always have a huge number of integral points. Well, there are some explanations. Thank you for your attention.